We're going to continue on looking at the electrochemical driving force. In the last lecture, we left off talking about the electrical driving force for ions. And remember, if they are going in the same direction, so maybe the chemical and electrical driving force are both going into the cell, that's easy because when you add them together, then the electrical chemical driving force will also be going into the cell. But if you have the electrical and chemical forces going in opposite directions, so maybe chemical is going in and maybe electrical is going out, we can't tell which direction the electrochemical driving force is going because it depends on which of those two forces is bigger. So we need a little bit more information to figure out which one is bigger and is going to win, and that'll be the direction that the electrochemical force will be going. So the piece of information we need to know is the ion's equilibrium potential. The equilibrium potential for an ion is defined as the membrane potential when the electrical driving force is equal and opposite to the chemical driving force. So we have a picture down below showing the equilibrium potential for potassium, which is minus 94 millivolts. So if the membrane potential of the cell is at minus 94 millivolts, then potassium is going to be at equilibrium, meaning that there's going to be no net movement of potassium in or out of the cell. And that's because the chemical driving force is the same size but opposite direction of the electrical driving force. So they cancel each other out, and the electrochemical driving force, when you add those two together, is going to be 0. So potassium is not going to move one net direction or the other. The Nernst equation is used to calculate the equilibrium potential for an ion. So this is a really important equation in physiology. So we're just going to explain how this equation is used, but I'm not going to make you actually do any calculations with it. So the 61 millivolts, that's just a constant. And then the Z, that's just the charge on the ion. And then we're going to multiply that by the log of the concentration of the ion outside the cell divided by the concentration of the ion inside the cell. So here we have the example of the Nernst equation being used to calculate the equilibrium potentials for sodium and also for potassium. So you can see that the equilibrium potential for sodium is plus 60 millivolts. And so if the membrane potential is at plus 60 millivolts, then sodium would be at equilibrium, and there would be no net movement of sodium in or out of the cell. And then the equilibrium potential for potassium is at minus 94 millivolts. And so if the membrane potential is at minus 94 millivolts, then potassium is at equilibrium, and there's no net movement of potassium in or out of the cell. And this link down here is really nice. It's just a little video, a little animation that walks you through the Nernst equation. So this is really important to remember and understand. So when the cell's membrane potential is the same as the ion's equilibrium potential, that means that the ion's at equilibrium and there's going to be no net movement of the ion in or out of the cell. So the ion's chemical and electrical forces are equal and going in opposite directions, and so they cancel each other out. And so the electrochemical driving force for that ion is equal to 0, and that's why there's no net movement of that ion. But if the cell's membrane potential is not at the ion's equilibrium potential, then the ion will move. Okay, and that's where we're going to compare the equilibrium potential to the actual membrane potential and figure out if the electrical driving force has gotten bigger or smaller than when the cell was at the equilibrium potential. So we're going to do some examples and show you how this works. Here's just a few pictures from your book. The one on the bottom left is showing the chemical driving force larger than the electrical driving force. So when you add those two together, you can see that the chemical driving force wins, and so the electrochemical driving force will be out of the cell. And the picture on the right, the electrical driving force is larger than the chemical driving force. So when you add those two together to get your electrochemical driving force, electrical driving force being bigger wins, and so your electrochemical driving force will go into the cell. All right, so let's just do some examples here. And we're going to start with sodium first. So I've got on the top the calculation for sodium's equilibrium potential. So that's the Nernst equation. So we just plugged in the numbers. We've got the constant 61, and then we just divided by +1, which is the charge on a sodium ion. And then we're going to multiply that by the log of the concentration of sodium outside the cell, which is 145 millimolar, divided by the concentration of sodium inside the cell, which is 15 millimolar. And when you calculate that out, the equilibrium potential for sodium is +60 millivolts. So we're going to start by setting our membrane potential to +60 millivolts, which is the same as the equilibrium potential for sodium. So we're going to draw our concentration gradient for sodium here. So sodium is higher outside the cell than inside. And our membrane potential being +60 millivolts, we're going to draw positive charges inside the cell. And then we're going to draw our chemical and electrical driving forces. So remember, the chemical driving force, that's just your concentration gradient. So sodium likes to move down its concentration gradient, going from high to low concentration. So it would move into the cell. And then the electrical driving force, we're looking at just the charges. So sodium has a plus charge. And then the membrane potential, the charges inside the cell here, we've got positive charges. Remember that like charges repel each other. So this sodium that's inside the cell would want to leave, and the sodium that's outside would not want to come in. And we're going to draw this arrow the same thickness as the chemical driving force, because we know that word equilibrium. So remember, by definition, when the cell's membrane potential is the same as the equilibrium potential, we know that the chemical and electrical driving forces are the same size, but they're going in opposite directions. So when you add these two together, they cancel each other out, and so your electrochemical driving force would be 0. And so there's going to be no net movement of sodium one direction or the other. Okay. All right, but let's say that sodium is not at +60 millivolts. So let's change, and let's say that our membrane potential is now maybe at +80 millivolts. So what I do to show the difference in the membrane potential, +80 millivolts, we have more plus charges than we did at +80 millivolts. So I'm going to draw more pluses inside my cell to show a higher positive membrane potential than at +60 millivolts. We're not going to change the concentration gradient at all, so the amount of sodium stays the same. So the chemical driving force will stay the same, so that'll be the same thickness as at equilibrium. And the electrical driving force, though, has changed, because we've changed the number of charges from the membrane potential. So at plus 80 millivolts, there's a lot more positive charges inside the cell than there were at plus 60. So sodium says, oh, I want to get out of the cell even more than I did at plus 60 millivolts. So we're going to draw that electrical driving force even thicker than it was at plus 60 millivolts. So when we add these two together to get the electrochemical driving force, you can see that the electrical driving force is larger than the chemical driving force. So the electrochemical driving force would be out. So at plus 80 millivolts, sodium would move out of the cell. All right, and let's say that instead of plus 60 millivolts, maybe our cell is instead at plus 20 millivolts. Okay, so that's our membrane potential. So if we compare that to when we were at the equilibrium for sodium at plus 60 millivolts, so we have plus 20 millivolts. We don't have as many positives as we did at plus 60 millivolts. Okay, and the amount of sodium is the same. We haven't changed that. So our chemical driving force is the same. We're going to draw that as the same thickness as what we had at equilibrium. And the electrical driving force has changed because we've changed the membrane potential. Okay, we have less positives at plus 20 millivolts than we did at plus 60 millivolts. So sodium still wants to leave. Okay, the plus charges still don't want to be together, but it's not as in a hurry to leave at plus 20 millivolts as what it was at plus 60. Okay, just because there's not as many plus charges at plus 20. So when we add the chemical and electrical driving forces together to get our electrochemical driving force, you can see that the chemical driving force is bigger than the electrical driving force. So the chemical driving force wins, and at plus 20 millivolts, the electrochemical driving force would be directed into the cell. So sodium would move into the cell at plus 20 millivolts. Okay. All right, and let's put our cell at the resting membrane potential. Let's say we're at minus 70 millivolts. So we would draw minus signs inside of our cell. And we're going to have the same concentration gradient as before. So our chemical driving force stays the same as what we've had all along. So it still wants to go in. And then our electrical driving force, sodium with the positive charge wants to be around those negative charges because opposite charges attract each other. So the electrical driving force would go into the cell. And because they're going the same direction, that makes it really easy. So the electrochemical driving force would also go into the cell. So at minus 70 millivolts, sodium would want to go into the cell. Okay, let's look at potassium. So I put up on the top the Nernst equation to calculate the equilibrium potential for potassium. So we have 61, that constant. The charge on the potassium ion is plus 1. So we'll divide 61 by 1. Multiply that by the log of the concentration of potassium outside the cell, which is 4 millimolar. And then divide that by the concentration of potassium inside the cell, which is 140 millimolar. And if we do the math on that, the equilibrium potential for potassium is minus 94 millivolts. So if we were to set the membrane potential at minus 94 millivolts, which is the same as the equilibrium potential for potassium. Okay, so the membrane potential, we would draw negative signs in here, indicating that our membrane potential is negative. We'll draw our concentration gradient for potassium. Potassium is always higher inside the cell than outside. And then our chemical driving force, looking at the concentration gradient. We're going to go from high to low concentration, so it wants to go out of the cell. And then the electrical driving force, we have a plus charge on potassium. We have negative charges inside the cell from the membrane potential. Opposite charges attract each other. So the potassium outside would want to go in, the potassium inside would want to stay inside. So the electrical driving force would be inward. And it's going to be the same size. So we're going to draw out the same thickness as the chemical driving force, and that's because we're at the equilibrium potential. So when we add these two together, they're the same size, going opposite directions, they cancel each other out, and so your electrochemical driving force would be 0, and so there'd be no net movement of potassium into or out of the cell. Okay, so if potassium was not at its equilibrium potential, it will move. So let's say that our membrane potential is at minus 100 millivolts instead. So if our membrane potential is at minus 100 millivolts instead of minus 94, minus 100, you have more negative charges inside the cell than you do at minus 94. So we're going to draw more negatives. The concentration of potassium, we haven't changed that. That stays the same. So our chemical driving force will stay the same strength. So that doesn't change. So we'll draw that the same thickness. But our electrical driving force has changed because we've changed the amount of charges from our membrane potential. So we've got a lot more negative charges inside the cell at minus 100 millivolts than we did at minus 94 millivolts. So potassium, with its positive charge, is going to want to go into the cell even more than it did at minus 94 millivolts because there's even more negative charges at minus 100 millivolts than there was at minus 94 millivolts. So we're going to draw our electrical driving force a lot thicker than we did at equilibrium at the minus 94 millivolts. So you can see that our electrical driving force is larger than the chemical driving force now at minus 100 millivolts. So when we add those two together, electrical driving force wins. And so our electrochemical driving force will go into the cell, and potassium will move into the cell at minus 100 millivolts. Okay, and let's do one more example. Let's say that we set the membrane potential to the resting membrane potential at minus 70 millivolts. So when I draw my membrane potential, we're going to draw not as many negatives compared to what we had at minus 94 millivolts, because minus 70 millivolts we have less negative charges than we did at minus 94 millivolts. We haven't changed the amount of potassium at all, so that's the same. So our chemical driving force, that doesn't change. We're going to draw the same thickness as what we had at equilibrium. But our electrical driving force has changed because we've changed the number of charges from our membrane potential. So now we have fewer negative charges inside the cell than we did at minus 94 millivolts. So potassium still wants to go into the cell to be by those negative charges, but it doesn't want to go in as much as it did at equilibrium at minus 94 millivolts. And that's because there's not as many negative charges. Okay, so we're going to draw a thinner arrow telling us that, hey, that electrical driving force is not as strong as what it was when it was at equilibrium. So now you can see the chemical driving force is larger than the electrical driving force. So when you add those two together, the chemical driving force wins. Oops. And so your electrochemical driving force will go out of the cell, and so at minus 70 millivolts, potassium will leave the cell and move out. Okay, so the key to these problems is you've always got to draw the cell at equilibrium first, because that's when you know when the chemical and electrical driving forces are the same size but going in opposite directions. And then you can draw the cell when it's not at equilibrium, and then you can figure out the relative size. Okay, so let's do some more examples here. Okay, so here we've got ion X plus, giving you the concentration outside and inside the cell, and I've given you the equilibrium potential. And we want to figure out if the membrane potential is at plus 10 millivolts, what direction is the electrochemical force? Okay, so the first thing you always want to do with these problems is draw the cell with the membrane potential set to the equilibrium potential. So we were given that for this ion, the equilibrium potential is plus 20 millivolts, so that's what we're going to draw first. So we're going to draw some pluses in here, and then we're going to set up our concentration gradients. And we know that we've got more on the outside of the cell than we do inside the cell. Okay, so the chemical driving force, looking at the concentration gradient, it wants to move into the cell down the concentration gradient, going from high to low concentration. And then the electrical driving force, looking at just the charges, we've got a plus charge on the ion, and then we've got these positive charges inside the cell from our membrane potential. And remember that like charges repel each other. So this positive ion inside the cell wants to leave, and the ions on the outside do not want to come in. So our electrical charge would be directed outwards. Okay, and we're going to draw this the same thickness as the chemical driving force because the cell is at equilibrium. So we know that these are equal and opposite, and when you add those two together, the electrochemical driving force would be 0, and there'd be no net movement of this ion, and so it wouldn't move, one direction or the other, no net movement. Okay, so you always want to draw that first, and now we can answer the question. So the question asks, well, if the cell is at a membrane potential of plus 10 millivolts, what would be the electrochemical force direction? Okay, so the membrane potential is at plus 10 millivolts, so we're not as positive. So we're going to draw less positives inside the cell. We haven't changed the amount of the ions, so concentration gradient is the same. So we're not going to change our chemical driving force, so that thickness will stay the same. But we have changed the amount of charges on the membrane potential, so our electrical driving force will change. So we still want to move out of the cell. Okay, those like charges still repel each other. But if we take a look at the amount of charges, we have fewer positive charges inside the cell from the membrane potential at plus 10 millivolts than we did at plus 20 millivolts. So Ion X plus doesn't want to leave the cell quite as much at plus 10 millivolts as it did at equilibrium at plus 20 millivolts. So we're going to draw our electrical driving force with a thinner arrow because it doesn't want to leave quite as badly. So you can see that the chemical driving force is larger than the electrical driving force. So when you add these two together, your electrochemical driving force will be into the cell, and at plus 10 millivolts, the electrochemical driving force will be into the cell, and so the ion will move into the cell. Okay, and then just one more. We've got an ion, A minus. We've got our concentration there, and we've got our equilibrium potential. And the question is if the membrane potential is at plus 80 millivolts, what direction is the electrochemical force? So first thing is you always want to draw the cell at the equilibrium potential. So we're going to set it at plus 45 millivolts because that was the equilibrium potential given to us. And then we'll draw our equilibrium potential here. So we'll draw some pluses there, or sorry, membrane potential. So we'll draw some pluses there. And then we're going to draw the concentration gradient. So we've got more of our ion inside the cell than we do outside. Okay, so the chemical driving force is going to be directed outside. So going from high to low concentration. And then the electrical driving force will be directed into the cell because the opposite charges attract each other. So the negative charge on this ion is attracted to the positive charges inside the cell from the membrane potential. And we know that this electrical driving force is the same size as the chemical driving force because we're at equilibrium. So when you add these two together, they cancel each other out, and your electrochemical driving force is 0, and there's no net movement of this ion in or out of the cell. Okay, so now we can finally answer the question up here. So we want to know the direction of the electrochemical force when the membrane potential is at plus 80 millivolts. So we're not at equilibrium. So we'll draw the membrane potential first, and being at plus 80 millivolts, we know that we've got a lot more plus charges inside the cell than we did at plus 45 millivolts. And then our concentration gradient, we haven't changed that, that's the same. And so our chemical driving force is the same. So we'll draw that the same thickness as what we had at equilibrium. But we know our electrical driving force has changed because we've changed the membrane potential. There's a different, there's more positive charges now at plus 80 millivolts than there was at plus 45 millivolts. So with more plus charges inside the cell, we still want to go into the cell with our electrical driving force, but we want to go into the cell even more than we did at plus 45 millivolts, just because there's even more positive charges. So you can see that the electrical driving force is now bigger than the chemical driving force at plus 80 millivolts. So when you add these two together, the electrical chemical driving force is going to go in because the electrical driving force is bigger than the chemical driving force. So to answer the question, the electrical chemical driving force is into the cell, and so at plus 80 millivolts, this ion would move into the cell.